Hello everyone, what's up? Today I want to show you Hi everyone, today I want to show you how we can solve this differential equation up here. This is just going to be some simple practice using the integrating factor method. I hope you can identify that that is the method we can use to solve this equation up here. So let's begin. So we know to use the integrating factor method, we're going to multiply both sides of the equation by some factor k, let's say. But before, let me define k like this. Let's say let k, our integrating factor, be a function of x such that, and then we know the property that we care about the integrating factor is that its derivative times y should be equal to the right hand side of our differential equation, which in this case is going to be 6k e to the 3x, okay? So remember, when we have the integrating factor, we want to say that this equation is true, okay? This is the property that will define our integrating factor. So now we just need to find k. And to do that, I'm going to multiply both sides of the equation by k. That will be useful, and you will see why in a moment. K dy dx minus 3ky is equal to 6k e to the 3x. Nice. Now to find k, remember we're going to differentiate this quantity on the left. So we have dk dx times y plus k dy dx. And this is equal to 6k e to 3x, which also happens to be equal to this. So we're going to say k dy dx minus 3k times y. So this is what we have now. Now notice we have two similar terms on both sides of the equation. They cancel out, and now we have I meant to write dk dx times y is equal to minus 3ky. Now we can solve for k because this is a separable differential equation, and these y's actually they go away. So this is a very easy differential equation. This is dk divided by k, and on the right hand side we have minus 3dx. Now we can integrate both sides of this equation, and on the left we're going to have, I believe I'm going to continue up here, we have ln of the absolute value of k, and this is equal to minus 3x plus our constant of integration, which we typically let it be equal to 0 or 1, whatever is most suitable for us. Now we're going to exponentiate both sides. So if we exponentiate the left, we have k, and if we exponentiate the right, we're going to have e to the 3x, negative 3x. Okay? So that is our integrating factor. And now remember, once we have our integrating factor, we can do this. We can say that if we have this equation, we can integrate both sides with respect to x. So let's say we have dky divided by dx. We integrate with respect to x. That's a d. I'm sorry, it looks a little odd, but that's a d. And we also integrate the right hand side, which is 6k e to the 3x. Oh, did I miss k here? Oh no, we're good. Yeah, I was saying, oh, we have e to the 3x here, but our integrating factor is e to the negative 3x. So I got scared that maybe I missed a negative somewhere, but no. This negative comes from this minus 3y, and this positive 3 comes from this one up here, so we're good. And we integrate this with respect to x. Cool. Now we have this on the left hand side, and this is something we can write like this. We just have the dx's cancel out, and then we just have the integral of dky, and this is equal to the integral of 6k e to the 3x, which I'm actually just going to write, I'm just going to throw in the value that we have for our integrating factor, which is e to the negative 3x times e to the 3x, how wonderful, dx. On the left hand side we have ky, and here we have, well, we know these two factors will cancel out, and then we have the integral of 6, which is just 6x, plus a constant c. And now we just need to solve for y, so we just do algebra. We have 6x divided by k plus c divided by k, and we have y is equal to 6 divided by k. That is going to be, so when you write it like this is also equal to e to 1 over e to a 3x. And if we take the reciprocal of this quantity, which is the same as 1 over k, then we have 6 e to a 3x times x. Okay, that's an odd way to write it. I should have put the x before the e, but whatever. And then we have the same thing here. We have c times k, and that is c times 1 over k, which is going to be the same as c times e to a 3x. Now this is our solution. This is our general solution. And now, well, we may have some initial conditions, and let's say we have, I don't know, we can just say at y equals 0, so let's say y evaluated at 0 is going to be y naught. And now let's see what that would be. So this means that we get y naught when x equals 0. So 6 times e to the 0, that is 6. Oh, well, actually, if x is equal to 0, this entire term vanishes, so just forget about that term. And then we have c times e to the 0, that is c. So we have y naught. And then that means that our final solution, our particular solution, if you have an initial value of y at x equals 0, should be 6x e to the 3x plus y naught e to the 3x. Okay? So this is a very nice and clean solution. I like it. This is what we have. Okay? This is our particular solution for this initial set of conditions, but you're done. If you get to this point, you're basically done. Okay? So this is how you can solve this differential equation. I hope this has been some useful practice, and I hope to see you in the following video. Bye.